On behalf of all of us at the National Glass Association, thank you for making time in your day to join us for this month's installment of Thirsty Thursday. It's back to business. NGA is pleased to announce that Glass Build America is on schedule for September 13th to 15th in Atlanta, Georgia, back at the Georgia World Congress Center. This its 18th year. Attendee and exhibitor safety is always a priority and will be elevated this year. Presented by NGA along with association sponsor, the Fenestration and Glazing Industry Alliance, Glass Build America is a comprehensive and united event connecting the glass and fenestration industry to share common challenges and solutions. Registration for the trade show will open June 1st. For exhibiting information, contact Jonathan Watson now at the email on your screen. This course is accredited by NGA for 1 hour of AIA elective credit. Certificates of completion are available upon request. An email will be sent immediately following the conclusion of this webinar with instructions on how to pursue credit or a certificate of attendance. It will also include a very brief survey on the session, and we thank you in advance for taking just a minute to complete that. We will address all questions at the end of the presentation, but feel free to submit them anytime using the chat feature in your Zoom toolbar. I'm now pleased to introduce our speaker, Helen Saunders. Helen has 25 years experience in the glass industry and is a general manager at Technoform North America. She currently serves as the president of the Facade Tectonics Institute and also acts as the energy technical liaison within NGA's fabricating committee. Helen is an advocate for high performance fenestration. She has been named one of US Glass Magazine's top 100 influencers and recognized as one of the top women leaders in the glass industry. She has a PhD in surface science from Cambridge University of England. Helen, welcome.
Thank you very much. Appreciate that, Sarah. So thank you so much, everyone, for taking time out of your day to listen to me this afternoon. I'm hoping it's going to be useful in helping ask the right questions and in making informed decisions about glass and glazing specification through the lens of embodied carbon. The presentation is going to focus on strategies for minimizing embodied carbon in buildings and specifically related to glass and glazing used in facades. And in particular, the focus is going to be on interpreting environmental product declarations for glass and what implications this data has for design and supply chain choices. So in terms of what we're going to talk about today, firstly, we're going to look at the difference between embodied and operational carbon and really why we should care. And then we're going to look at the big picture for an embodied carbon in buildings and where the big levers are for making a difference in embodied carbon emissions. Then we're going to look at environmental product declarations and the precision of the data reported in those, and then take a deep dive into some EPD data for insulating glass and flat glass. We're going to identify some key takeaways from this data and then provide 5 ways to impact the embodied carbon in facades. So without further ado, let's dive into the difference between operational and embodied carbon. So operational carbon is the carbon emissions that is produced by operating buildings. It's really what we've been focused on for many years through operational energy reductions in buildings, which is mandated by our building energy codes and standards. So this is what we're used to focusing on as we design and specify buildings. So what's embodied carbon? Well, it's all the emissions, all the carbon dioxide emissions or the equivalents of carbon dioxide that are emitted during the sourcing, the manufacture, the transportation and installation of materials at the manufacturing site, the building construction site. And unfortunately, I don't really know where embodied came from because it's not like it's captured in the materials that you're producing. Those emissions are long gone in the atmosphere causing warming. And a gentleman called Lloyd Alter suggests that really we shouldn't really call it embodied carbon, it should really be renamed as upfront carbon emissions, because it really reflects the immediacy of the fact that it's being emitted right now and causing an immediate real-time impact. So don't be confused by the fact that of the word embodied. It means quite the opposite. So, why should we consider embodied carbon? Well, this is some data from UN Environmental Global Status Report in 2017, and it gives you the share of energy-related carbon dioxide emissions by sector. And you'll see that building materials and construction, or what we call embodied carbon, contributes 11% of the global carbon emissions, energy-related carbon emissions. Now, operational carbon contributes 28%. Now, if you add that up, that's almost 40% from the building sector. And so 11% of that 40 is 28%. And so embodied carbon emissions is about contributing about 28% of all building sector emissions. So it's pretty significant. And it's becoming more significant because the rate of emissions from construction is accelerating, because the rate of construction is accelerating. Architecture 2030 estimates that the equivalent of one New York City is being added to our planet every 34 days. And this will continue at this rate for the next 40 years. We're going to double the current global building stock by 2060. And between now and 2050, the total embodied carbon emissions is actually going to equal the operational carbon emissions. So again, why should we care so much about embodied carbon now? Well, this graph shows the carbon emissions as a function of time over the last few decades. And you can see trend lines, the red one for emissions if we continue as business as usual. And then the green line, you see, this is the path that we must take if we're going to limit global temperature rise to 1.5 degrees C. So you can see we absolutely need to take action, and we need to take action now. And this is really where the time value of carbon comes in. Just like the financial concept of time value of money. Since these emissions are occurring at the beginning of the building life cycle, the impact on the near-term emissions for the building is actually more significant than that 11% that we just talked about implies. And the timing matters because, as you can see from the graph, we have to curb carbon emissions and quickly. And we just talked about the rate of building construction accelerating. And when we look at the rate of carbon emissions, it's still growing globally. And we're seeing energy use and carbon emissions leveling off in developing countries, in developed countries, but we're seeing significant growth in the developing economies of, say, India and China, which are where the economies are still very much fossil fuel based. So I hope I've convinced you about why we should care about embodied carbon and do something about it now. So with that said, let's look at the big picture impacts in a building. Now, this is a framework which is not, the diagram here is not to scale. It's really just an illustration of where the biggest levers are in the building for carbon reduction. Now, the most sustainable building is really the one that isn't built. So we really should stop building, but really, realistically, there is not going to be a moratorium on building construction anytime soon. So if you are going to build, if you need to build, then the best thing to do is to retrofit rather than to actually create something new. If you have to build, then smaller is better. Obviously, and if it's smaller, then not only are you going to have smaller embodied carbon impact, you'll also theoretically have smaller operational emissions as well. And then the next thing, most important, is to make it last a long time. If you're going to invest in all that embodied carbon in building your building, you better make that investment last. So if building is necessary, the most impactful decision is embodied carbon. And one thing I want you to take away from this is that service life is important. And when you're looking at embodied carbon, you really should divide the embodied carbon by service life to get an equivalent carbon impact. Because a product with half the emissions but half the lifespan is not better than one that you're comparing it to. So embodied carbon and lifetime have to go together. So one of the things that we can think about as we're extending building service life is what, and especially when we're looking at facades, what does 100 or 200 or 300 year building lifetime look like? What will it mean to the technologies and how we build facades? What about, what would it mean to make something upgradable, to a curtain wall maintenance? And how do we extend insulating glass unit service life? And when we took a single pane of glass that has been used for many years, which arguably has a lifetime in the thousands of years, and we turned it into an insulating glass unit, which obviously had much better operational performance, but turned it into a product that has a lifetime in decades, not thousands of years. So lifetime is really important. Then if you have to build, then typically you look at the structure, because the majority of the impacts of a building come from its structure, primarily in the cement and in the steel. The steel typically is about 30%, and the concrete is about 50%. So really significant impacts in the structure. And then you want to be looking at the durability of the system. And for steel, and I'll talk about this in a moment with aluminum, there's really an important aspect here in steel sourcing, primarily because of the use of renewable energy to create that steel, which makes for a lower embodied carbon system. And then after you've looked at the structure, then you can look at the enclosure. Typically the enclosure contributes about 15% to the embodied carbon of a building. And this goes, and we're going to take a deep dive into the glass part of this. But typically, again, you want to be looking at durability, how long it will last. And then for aluminum, again, domestic sourcing, because most domestic sources that are made through hydroelectricity, which is obviously a low, a green and low embodied carbon fuel. And then we can look at other sources after that. But this hopefully gives you some idea about where the biggest levers for embodied carbon in buildings are. So just really to sum up here, if you must build, extending the service life is the most important consideration, because of all that investment you're going to make in embodied carbon. You really need to leverage it over the longest period of time you can. Now, if you have to build, let's look at this diagram here. This is an example of an embodied carbon assessment that was done of an office building by Anthony Pack of Preopta. And it really demonstrates where the largest contributors are in the building. And you can see the majority of it is coming from the concrete, about 50%, as I mentioned before. And then steel, rebar, structural steel, other steel and iron. And a read of Bill Gates's book, How to Avoid a Climate Disaster, will give you a really good layman's explanation of why these two materials take the top spot for embodied carbon. basically, they both use fossil fuels in the creation of the material, and they emit carbon dioxide through the chemical reactions that are carried out during their processing. So it's kind of like a double whammy. But I would recommend Bill Gates's book, really a very good read. Anyway, the majority, you'll see that on the right-hand side, aluminum is down there at 6.9%. And having talked to Anthony, the majority of this comes from the curtain wall. And then you'll see underneath it, glass is about 1.8%, 1.9%. Now, of course, the actual impacts of that you'll see in a particular building will depend on the specifics of a building. This is just an example, and it'll depend on the building size and the massing and the window area and the type of structure, but it gives you a sense of the order of magnitude. And I did verify some of these numbers with Ted Kessick, who's a professor at the University of Toronto. And he basically tells us that about 10% for a total curtain wall, aluminum plus glass, is a reasonable estimate for the impact of a curtain wall in a building. But again, everything is dependent on the design, but this is just kind of an order of magnitude. So it reinforces that if you must build, the biggest issues are related to minimizing the impact of concrete and steel, and of course, maximizing the lifetime of the building. And as we're going to see in a couple of slides, aluminum production, while it's energy intensive, doesn't have to be carbon intensive if you make it from renewable energy sources and if you use a lot of recycled content. So of course, this number can be reduced. So let's talk about an environmental product declarations. You've probably heard the acronym EPD bandied around. Maybe you've even been asked for one, or you've asked a fabricator for an EPD. It's short for Environmental Product Declaration, and it's kind of like a food nutrition label for a building, except that it reports the environmental impacts of making a product. An EPD is really a life cycle assessment of the manufacturing of a product according to a set of rules, and these are published rules called Product Category Rules, or PCR. And it reports global warming potential, often you see called GWP, and typically it's in kilograms of carbon dioxide equivalents. That's because not all greenhouse gases are carbon dioxide. Methane is a very strong, potent greenhouse gas. And what they do is they scale it, the emissions, to a kilogram of carbon dioxide and the impact that that has on the environment. So there are typically two different scopes for an EPD: a cradle to gate, which means it takes into account the impacts of the supply chain through the manufacturing process and to the end of that process, to the manufacturing gate. Or cradle to grave, which includes those impacts, plus includes the life of the material and its disposal. Typically in the glass and glazing world, our EPDs are typically cradle to gate. So they don't include transportation to the job site or any service life considerations. Now, before we start digging into the EPD data for fabricated glass, I'm going to take a diversion into precision. We really need to understand the precision of the data that's reported in these EPDs to make sure that we understand what when data in one EPD is significantly different from another, or whether they're basically the same. And there are really wide margins of error in the data that are reported, and that they derive from a lot of averaging that's done in creating in pulling the data and analyzing the data. There's averaging over different manufacturing sites. There's averaging over multiple product configurations. There's averaging over different manufacturers in the case of an industry-wide EPD. There's averaging across mixed supply chains. And then there's also the error in estimates that are made in the process of gathering data and allocating to different product lines. And then there are differences in data that exist in the different software tools that are used to calculate the global warming potential, for example. In fact, somebody just told me recently that they submitted the same data set to 2 different practitioners using 2 different LCA software tools. And the numbers, the global warming numbers that came back were very different from each other. So best case, the margin of error is about plus or minus 20%. That's best case. And that would be if the data was from a single facility. It was supply chain specific. It was a single product configuration. But typically, we can expect much higher or wider margins of error, up to or higher than 40%, for example. So it's really important to bear this in mind when you're interpreting data in an EPD. So before we dive into the EPDs for glass, I want to take a bit of a detour to aluminum and some data which has some really interesting implications for fabricated aluminum sourcing. So just like North American steel I mentioned is typically made with electricity and with cleaner grids than foreign steel, that means it has a substantially lower carbon footprint than imported steel. The same is actually true of the energy intensive aluminum that's used in curtain wall and window systems. In the US, as you can see from this chart, aluminum production operations typically use hydroelectric energy, which is very green with very low carbon emissions. But if you look at this chart, which shows the power mix for primary aluminum smelting globally, you'll see that aluminum made in China or in the Middle East is typically used for coal, typically made from electricity produced from coal or natural gas, which is very carbon intensive. So aluminum made from hydropower has a much lower carbon intensity than that made from coal-powered plants. So what that means is for aluminum, the most impactful way to reduce the carbon footprint of aluminum facades is to specify domestic sources from hydropowered manufacturing plants and also with a high recycled content. So that's your kind of rubric for getting the lowest emissions in aluminum. And as an interesting side point, since EPDs have become available for fabricated steel products, it's become apparent to the design community that the biggest impacts from for steel are from the source, from the mill, the steel mill. And so the focus is now on looking at the mill impacts for steel, and architects are no longer asking for EPDs for downstream fabricated steel. They're just asking for the mill information. And the same may be true for aluminum used in curtain wall and window systems in the future, with the focus being more on the aluminum source and the recycled content rather than the fabrication process impacts. So let's now dive into the impacts of processed glass or insulating glass. The graph here shows the relative contributions to the global warming potential of low E insulating glass, and this was derived from a published North American EPD. This is from Vitro's processed glass EPD. The blue bar that you see, the big blue bar, is the contribution from making the float glass. The green bar is from the coating process, the low E. The red bar is the contribution to the heat from the heat treatment process to heat strengthen or temper. And the purple bar is for the IGU manufacturing process itself. So what you can see here is that about 75% of the impacts, the global warming potential, comes from the float glass production. About 13% from heat treatment and 10% from the IGU process itself. And if you dig down a little bit further into the IG process, about half of those impacts, or about 5% overall, comes from the electricity used to run the insulating glass unit line, manufacturing line, and then the other half comes from the IGU materials themselves. Now, the quantity of emissions from electricity is typically dominated by how clean the electrical grid is in the location where the factory is. So there isn't much a fabricator can do about that because they're located where they are. And of course, factory efficiencies can help in the margins, but it's primarily dominated by the grid mix. And of course, in materials, there's a between fabricators and of course, relative to the specification, typically the same type of materials are used from fabricator to fabricator in the same kind of quantities, but of course, because of course you need a certain quantity in order to deliver a durable insulating glass unit. So one of the key takeaways from this is that the impacts of making the insulating glass unit are relatively minor compared to the impact from making the float glass itself. So what does this mean? Now, to me, this says that if I'm a designer, I shouldn't compare EPDs for insulating glass units between IGU fabricators to make supply chain decisions, because it's just not meaningful. And the reason I say this is multiple. One is because as you saw, the IGU manufacturing impacts are really relatively minor compared to the rest of the building structure. It's about 0.2% of the overall building's global warming potential. That's like, we saw that 2% of the building structure was glass, the impacts on the building structure was glass. And we know that 10% of the insulating glass impacts are from the IGU manufacturing process. So 2% times 10% is 0.2. So there's only a very small impact in the overall scheme of things in the building scale. The float glass impacts dominate. And in fact, that 10% of the total impacts from insulating glass is within the margin of error of the float glass variation that you might expect, as I mentioned before, the plus or minus 20% minimum. Then, as we talked about before, IGU fabricator location drives the energy-based emissions because of the grid mix. There's also, when you're thinking about this, proximity to the job site needs to be taken into account too, because the EPD doesn't include that. And again, the 5% of 2% is very small in the margins. It's not where the low-hanging fruit is for carbon-based decision-making. And then if you look at the IGU materials, of which they're 5% of the IGU impacts, the materials are basically defined by the design and the specification. They're the same or very similar across all fabricators, especially in commercial. PIB silicone is ubiquitous. And you can't skimp on those because you need it to deliver the service life. So from an IGU perspective, EPDs don't help us drive our carbon-based decision-making, certainly not from a choosing your supplier perspective. So the question I would ask then is, should we just focus on the flat glass supply chain? Should we be choosing our or flat glass supplier based on the embodied carbon of their flat glass. So let's take a deep dive into that data. I've plotted here all the global warming potential data for every publicly available EPD for flat glass. It includes the industry-wide EPD for flat glass, and it includes individual manufacturers that have published. You can see the data points there. You can see the mean. I put in these lines here, which is the mean plus or minus 3 standard deviations, which for those of you who are familiar with statistics, typically if you have a normal or Gaussian distribution of data, 99.7% of the data is within plus or minus 3 standard deviations of the mean. So what this means based on our North American data, there's a 99.7% chance that the global warming potential of any piece of flat glass lies in the range that I show you with these red dotted lines. Now the error, as I mentioned before, the precision in this measurement, the margin of error is at minimum plus or minus 20%. And I've marked these on the graph here. And so you can see the conclusion from this data is that all flat glass in North America appears to have basically the same embodied carbon within the margin of error. So that tells me that you shouldn't use flat glass supply chain as a carbon reduction strategy either, because they're all the same. So what should we do? Well, design is really the driver. And as I'll talk about in a moment, most of the embodied carbon is already decided by the time the design has been done. And here's an example of a design driver. This is the global warming potential difference between a triple pane and a double pane IGU. As you might expect, the addition of the third pane is what's driving the additional embodied carbon of a triple pane over a double pane. That's the biggest driver there. It's not the additional sealant materials or spacer materials. It's all about the third pane. So when you're looking at considering a triple pane to reduce your operational carbon, you really have to weigh that against the impact in the embodied carbon. So that's an important evaluation. And you also should think about potentially the difference in service life that you might expect between a double pane and a triple pane, because as many of you know, when you double the cavity size, you increase the edge seal stress in the edge seal, which can potentially have an impact on service life. So the question really remains about, whether we should use EPDs for glass that we see for glass to make supply chain decisions. And basically, I hope the data that I've shown you suggests that we shouldn't be using EPDs either for EPDs for IGUs or EPDs for flat glass to determine supply chain choices, because it doesn't matter. By the time the fabricator produces the IG, the major impacts have already been determined by the architectural design. The number of lights have been decided, the thickness of lights have been decided, the heat treatment of the lights have been decided, the glass area has been decided, the number of unique sizes and shapes have been decided. And the reason I mention that is that this determines fabrication efficiencies. The more uniformity that you can have in your design, the more efficiencies and therefore the less waste and scrap that the fabricator has, and that also impacts embodied carbon. So if you really want to impact embodied carbon in a facade, you have to start at the design. So what can we do to impact embodied carbon in facades? Number one, and I go back to what I said at the very beginning, you have to focus on optimizing service life. So when we think about service life of facades, we go directly to the insulating glass unit at lifetime. Got to make sure that your edge seal is carefully designed, it's well manufactured, and it's installed well. It's really important to focus on this, the design, the workmanship, and the installation. So look for fabricators with IGU certification, especially certification programs that require units to be made on a production line in front of an auditor to meet the ASTM E2190 standard. Look for margin in those durability tests. And avoid a lowest bidder wins approach to contracting, because this supports the goal by allowing fabricators to invest in higher quality materials and focus on quality production. We don't want to have this race to the bottom in terms of cost and quality. And I would also promote the use of an evaluation and an assessment of edge seal stress on a project level based on the unique size and IGU makeup for the project, to make sure that you haven't created very stiff units that have very high edge seal stresses. And this is something as an industry I would promote that we should do more of. So that's number one. Number two, I think I've said this before, locally sourced aluminum made from renewable electricity sources with a high recycle content. Should be easy to do. And, you know, for me, the light bulb went off. It's like, you know, you don't need tariffs to stop imported aluminum coming in. You just need a carbon specification. Number three is assess the life cycle value of triple versus double pane very carefully. Does the operational emissions benefit outweigh the embodied carbon impact? How many years before the operational energy savings offset the added embodied carbon? And can you reach the needed thermal performance with a dual pane, but maybe you're using a warm edge spacer and a much higher thermally broken frame? Are there other ways to get to that thermal performance you need? Other ways of reducing the impact of a triple pane? Should we be considering the difference in the lifetime, as I mentioned before? If there's increased edge seal stress over the dual pane, what's the impact on service life? And then fourthly, design with efficiency in mind. Design with a view to help fabricators reduce waste and improve their efficiencies by reducing the number of unique sizes, for example. And then look at whether your glass is over-engineered or not. Do all IGUs in your facade need the same makeup? Do they all have to have the same thickness as the biggest unit on your project? Do all lights need to have the same heat treatment? I mean, typically what we're doing on buildings is we're calculating or assessing the IG configuration based on the largest unit and the needs for the wind load, for example, which ends up, and then you replicate that configuration across all the units, no matter how small. Now you do that obviously because you want to have some aesthetic uniformity too, but do you have any, is there any scope for not having a one size fits all across the facade? And then number five, which is really, I struggle with EPDs because I think they're very useful tools. I think they're very useful tools for fabricators to see where the biggest impacts are in their business and in their manufacturing, and to help them reduce the impacts. But I struggle with them because they're very expensive, about $30,000 per product line, which is really expensive for small fabricators. And as you've seen from the data here, especially in insulating glass units, it doesn't give you new data to make supply chain decisions. So while we really want to find ways, we really want to encourage fabricators to reduce their carbon footprint, it would be good to find lower cost ways than a published EPD to allow them to demonstrate their commitment to reducing the environmental impact of their operations. So just to wrap up here, EPDs for glass and aluminum, at least from my perspective, can be very useful in determining the relative global warming impacts on a project scale when you're doing an overall life cycle assessment for a building. But they shouldn't be used, at least of process glass and float glass, as I've shown here, they really should not be used as a way of selecting your supply chain. Glass represents a single-digit percentage contribution to a building's embodied carbon, and all North American float glass impacts appear the same within the margin of error based on the data that we've seen. And the impacts from IGU processing are only 10% of the overall embodied carbon of an IGU. And it's really the design that bakes in most of the impacts before you even select the supply chain. And it's the design that should be the focus from an embodied carbon perspective. And then lastly, go back to, I'll get on my soapbox again about service life. If you're going to build, a focus on service life is the most important first consideration to drive down emissions in facades. So with that, I will open up to questions. I haven't seen anything in the chat because I've been so focused on talking, so I will stop now, and Sarah, maybe you can tell me if there are any questions.
Yes, sounds great. You do have a few questions. So starting at the top, and I believe this one came in around slide 15, if I recall, but 10% impact for curtain wall of the 15% for enclosure, or is it 10% of the total embodied carbon?
Sorry, did you say slide 15?
There it is, yes. Back 2, I think. There we go. So
yeah, 15% of the total building core and shell embodied carbon. That's what 15% is. So if we look at this, if we look at this diagram, we see that concrete is about 50, steel is about 30, the facade is about 15. So if you add to that, so 50 plus 30 is 80, plus 15 is 95, and then the rest makes up the remaining 5%. But again, this is plus or minus because every building is a little different. And this is why you see in some of the Pacific Northwest, you'll see these timber buildings going up because they're trying to reduce the steel content.
Okay, great. The next question, is this information on embodied energy or carbon for insulating glass versus raw glass going to be incorporated into LEED and other carbon counting programs for construction?
I can't necessarily speak for LEED or USGBC, but we have been talking to the Carbon Leadership Forum or the Building Transparency, who have developed the EC3 calculator. They have asked the glass industry to participate with them in refining their tool with respect to the Division 8 materials. And that will allow us to very clearly demonstrate where the impacts are. In fact, I think I mentioned that the steel impacts have become more transparent now, and that is actually in part due to the embodied carbon calculator from Building Transparency, because they've been able to identify and classify all the data from the industry available EPDs, they've been able to demonstrate where architects should be putting their focus. And that's what's now driving architects to ask for the mill information, not for the fabricated steel information, because they know that the majority of the impacts are due to the steel manufacturing, not the steel fabrication. So we have a joint group that I'm actually, just before we started the presentation, I was just talking to Urmila about where we were with getting the NGA task group together to participate with FGIA with the embodied carbon calculator folks. So I'm really looking forward to that, because I think it will really help drive architects to be, asking the right questions and not necessarily asking for EPD information at an IGU fabricator level.
Okay, great. We have two questions or comments, both related to double versus triple glazed IGUs. The first being, has an analysis been done to look at the impact on operational carbon?
Actually, yes, there has, but of course it depends on the building and it depends on the climate zone. So I think I mentioned Ted Keswick from the University of Toronto. One of his students has just published their master's thesis just on this topic in particular. And he says, at least in the climate zones that she evaluated, the triple wins over double. However, they have been assuming the same service life. So I've started a conversation with them about doing the analysis, a sensitivity analysis, to understand at what point service life would have an impact, or what service life difference would change that scenario, or change that, change the result that triple wins over double in those climate zones. So I can, if I know who that person is, I can send you the master's thesis. I have a link to it. Mm-hmm. If you have interest. But I think, to me, it's to understanding if there's any difference in service life and the sensitivity of service life to that analysis.
Okay, excellent. Let's see, we have a couple questions about service life. So what are the technical limits on glazing durability, and what could be achieved in terms of service life? And then can you also factor triple glazing into that response?
Can you repeat that again, just to make sure I understand the first bit?
Technical limits on glazing durability in terms of what can be achieved for service life.
Yeah, that's a good question. I mean, I think, typically you expect a service life for an insulating glass unit of 25, maybe 30 years. Plus or minus. And of course it depends on the IGU makeup, it depends on the application, and so many depends. I think ultimately the way we're building our insulating glass units now, there certainly is a limit. I'm not sure that we're going to find an insulating glass unit unless we change our technology lasting 100 years. But what we can do is we can do everything we can to maximize the service life that we get out of our existing technologies while we develop new technologies to extend the service life. So I go back to making sure that we're using the best materials we can, enough of the best materials we have, making sure that we have good process control and workmanship, making sure that we're doing project level assessments of edge seal stress. We can make these very stiff, very wide cavity units. We can't expect them to have the same service life as much larger, more flexible units. So when you go from a half-inch cavity, 6x12.6, 5 foot by 10 foot IGU, and then you make a small one that's got 2 half-inch cavities and 10 millimeter laminated plies, and then you make it you have the very small units at the end of the curtain wall that are maybe 1.5 feet wide. That's going to have a very high edge seal stress, and we should not have the same sealant height in those units as we have for the for units that have much lower edge seal stress. And I think that's a gap that we have in how we look at edge seals at the moment. And the folks from Simpson, Gumpert, and Heger and I have collaborated on a paper that just got accepted by ASTM, where we're proposing a methodology for creating a ASTM standard that would look at service life design for edge seal.
Interesting. Okay, it's great to know. With regard to triples, is it safe to assume that if a piece of thin glass was used for the central light, that the overall embodied impact would be minimal?
That's a very interesting question. 2 or 3 days ago, I would have said yes, because it's got less glass. But I've been educated to think that it's not quite as simple as less glass is less embodied carbon because of how thin glass is made on the float line. So I'm not the expert in that, and I would defer to the folks at NSG and others to comment on that. But typically you would expect less glass would be lower embodied carbon, but I'm not quite sure it's as linear as that.
Okay. And then a couple questions with regard to EPDs as well. If the primary benefit of an EPD is to help manufacturers assess and improve processes, why not just rely on the LCA?
And exactly, and that would be one of the ways that we could reduce the cost and not have an EPD requirement, is just have people do their own LCA, because an EPD is where you have a third party review it and rubber stamp it. Not rubber stamp, it's probably not the right way of saying it, but at least give third party verification. So if I believe in third party verification if you're having to use it externally and you need to make sure you have a level playing field. But if a manufacturer is just doing it to help improve themselves and they have enough expertise internally to do it, then I don't see why an LCA there's anything wrong with doing it using an LCA. Because an EPD is just a third party review of your LCA data.
Okay. And then as concrete and steel industries decarbonize, the contribution of glazing will proportionally increase. So without EPDs, how do designers send a signal to the industry that we need to lower embodied carbon in glass?
Okay, I'm just reading that just so. Yeah, I as I say, I think EPDs have their place. And I think individual, that there has to be mechanisms for the industry to demonstrate the impact of their product on the overall building construction. So I am not sitting here saying I don't believe EPDs are useful. I do believe EPDs are useful because they're useful in creating what you're seeing in front of us right now. What I'm saying is that we shouldn't use them to make supply chain decisions, supplier A over supplier B currently based on the data we're seeing.
Okay.
And I think that if we look at where the glass is there's certainly work to be done in decarbonizing glass. Electrification of float glass would be, would be an amazing, step change in the current state. But I don't know how far that is away. but that's certainly, that's certainly on people's minds. I've seen articles about the decarbonization of the float glass process and the move towards either lower carbon processes or switching directly to electrification. But that's certainly a disruptive technology. But again, I'm not an expert here. That I would leave that to our friends in the flat glass manufacturers to make comment on that.
Okay, excellent. Well, I think we've addressed all of the questions we received. We did have one comment that mentioned GANA's glazing guidelines, and just wanted to point out that is also in reference for how to properly install IGUs as a way to impact and extend service life. So that is a part of the glazing manual that's available in NGA's store, and that I believe is what that's referring to. So we hope you found this session beneficial. Recording of this presentation will be available in our on-demand webinars library in the coming days. NGA has additional resources that support what Helen shared today, and the links for each of those are also now in the chat. We hope to see you again on May 20th for the next presentation in our 2020 Thirsty Thursday series, which will address the latest with regard to standards for anisotropy, including the latest from ASTM. So thank you all for being here today, and Helen, thank you for sharing your time and expertise with us this afternoon.
You're welcome. If anybody wants to contact me, my email address is there. Feel free to reach out. It would be great to carry on the conversation.
Excellent. Thank you all. Have a good afternoon.